So let's talk about planes in space now. We talked about lines. Let's talk about planes in space. Before we do, I wanted to tell you there's actually yet another way to describe lines in a plane. It's important that you're in a plane, so 2D. I can't emphasize that enough. In 2D, okay, what you're seeing there. Then another way to describe a line is to, instead of give a vector, we gave a vector that moves along. Previously we talked about a vector v that's along the line. Well, what if instead we gave a vector that's normal to the line, perpendicular to the line, okay? Normal here means perpendicular to the line. So if you have a normal vector AB, we'll just say it's numbers A and B, then we could describe the line in the following way. We have, for any point R, this vector R in the darker blue there is a point. It's an arbitrary point on the line. It's arbitrary point xy on the line. Well, R minus R naught is a given point on the line. R minus R naught will be orthogonal or perpendicular to this normal vector, okay, which we're just given as AB. So what do all equations on this line obey? They obey the equation here, that the normal vector n is perpendicular to r minus r naught. And r minus r naught, if you can't see it clearly, is here. So for any point, I could have chosen, let's just say the point over here. Well, then what's r minus r naught? It would be the vector that points in this direction. And guess what? It's also perpendicular to that normal vector. So we could have instead given a normal vector and said that equations of the line respect this relation, that the normal vector is perpendicular to r minus r naught, or this vector here, which means what does that mean if they're perpendicular? That means their dot product is 0. Okay. So you could relate this back to things you might have run into, where if you simplify this expression, you will get y minus y naught is equal to negative a over b x minus x naught. Okay. And these a and b, it's no longer the case that a is the rise and run. You have this being perpendicular to the actual vector, that's the rise and run. That's why a is over b, and you have that minus sign there. So this would be relatable to the things you've worked on previously if you relate m, the slope, as equal to minus a over b. Minus a then would be the rise, and the run would be b. Now pause for a minute and think about why this only works in a plane. Okay? If you could figure out why this would only work in a plane, and that if we actually had a third axis that comes out, say the z-axis, that this no longer works. Okay? Why would this description of a line not work in space? It only works in a plane. So that given the normal vector is not sufficient to describe a line. Okay, so pause for a second and try to reason of why this wouldn't work in space, in that you wouldn't get a line. Okay, I hope you've thought about it for a minute and have come to the conclusion that this wouldn't work, to give a normal vector, because there are actually in space, because there are actually many vectors that are perpendicular to the normal vector that are not just on a line, but on many different lines. So here, here's our say green line that we had above. running like this. But if you were also along this line here or that line here, all of them on a plane, then all of those lines would, all of these lines would respect the relation that you see here. So this prescription that we worked on above in space gives you a plane and not just a line. It gives you a whole series of lines. And so that's how we will describe planes in this class. You have the normal vector n. It's perpendicular to the plane. Okay, so it's called the normal vector. It's perpendicular or orthogonal to the plane. And for any point r on the plane, so r is on the plane, it's this arbitrary point xyz that's on the plane, minus r naught. R naught is this purple point here. It's the given point. So they're going to respect this relation here. Okay, so if n is given as ABC and r minus r naught is what you see here, these knotted values are given. Then for any point on the plane, you're going to respect that relation there, which you could write out this way. Okay, this here is the equation of the plane that you get. Okay, and this is why this trying to describe a line this way in space just doesn't work, because you actually end up with a plane. So what are the two things that we need to describe a plane in space? One is a normal vector. Okay, that's one of the things that we need. And the other is a given point. Okay, if we have these two things, then we could get the equation of a plane. And notice this does describe a plane. I mean, once you specify x and y, z could be determined and that would give you a point along the plane. So what if you're not given a point in a normal vector? What if, for example, you're given 3 points, okay, and these 3 points are not collinear, so they don't form a line. They'll form a triangle, and that triangle will sit in a plane. Okay, so what if you're given 3 points and you want to get the equation of the plane that they sit in? How can you do that? Okay, we said above that you're going to need a normal vector and you're going to need a point. Well, we have a point. Okay, we have in fact 3 points, so getting a point is not a problem. Let's just, for the sake of simplicity, take the point P as our given point. Okay, so R naught, this given point here, is going to be the point P. We could have also chosen Q and R, no problem. And so our R naught will be 2 minus 2, 1. That fulfills this. And now we need a normal vector. And how will we get that normal vector? Well, suppose you then have, let's erase this business here. Okay, suppose you view, and I'm not drawing these accurately just for the sake of illumination. Suppose that's P, Q, and R. Okay, then get this. What I could do, or what we could all do, is get the vector PQ, okay? So that's the vector PQ here. And what we could also do is get this vector here, PR, okay? And both of those vectors lie in the plane. So what's the cross product going to do? What will the cross product do at that point? It's going to give us a vector that's orthogonal to both of those vectors. Okay? So if we take the cross product, it's going to point, say, PQ cross or let's do this in a different color here, that's going to be the vector PQ cross PR. Okay? Or we could have also chosen PR cross PQ. If we would have chosen PR cross PQ, we would instead get this guy here. Okay? But either one, the pink or the green, they're both orthogonal or normal to the plane, and both of them would work. So that's what we're going to do. We're going to compute PQ. We're going to compute PR. We're going to take the cross product to get this vector that's normal, and that's going to fulfill the second ingredient that we need to describe a plane in space. So that's how we do this. Here's our point. PQ, how do I find PQ? Well, by now we should be experts at this. You just take the x component of Q and subtract from it the x component of P. That's your 1 minus 2. Okay, so that's how you get PQ. Doing this for the rest. What about PR? You do the same thing. So here, say the Z component, that's going to be the Z of R, which is 5, minus the Z of P, which is 1. And we're going to take the cross product. Okay, you do the cross product by looking at this determinant, and you plug and chug and compute, and you end up getting a normal vector 8 minus 5, 11. And what then is the equation of the plane? It's going to be that whatever x, y, and z that respect this relation. So for R, we have x, y, and z. Our R naught, where did our R naught come from? 2 minus 2 and 1. It was just a given point. And so when we dot these two together and set it equal to 0, because that's how we stay on the plane, we have to respect that relation, we get this equation. Okay? And, you don't really have to write this preliminary part once you get, good at it. You could just jump and say x minus 2, why 2? Because that's the point, the x component of the P point. Or you could say plus 2, y plus 2, because that's minus this point here, right? So you got to be careful. It's x minus x naught, y minus y naught. And y minus negative 2 is plus 2. So that's where that plus is coming from. And z minus 1, why? Because of that. So you could write that right away. You'll still need to work out the normal vector, though. You're going to have to take the cross product to get it. And now you'll have this 8 here. You have this minus 5 there. And you have this 11 there. And so we now have our equation of the plane. Now, this was the easiest way to describe a plane in space. And, if you get confused easily, you don't have to listen to this next part. But I thought it might be useful to kind of see, try to relate it back with how we described lines. And remember, with lines, we didn't describe them with normal vectors. That was an additional part. That this was just something extra. You're not, for lines, you should only be thinking in terms of this formula in this class. I only talked about this just to introduce planes, okay? So we're not going to be looking at this description of lines. But you might say, well, look, you gave vectors that are along the line here. Why don't you give vectors that are along the plane, right? Why don't you give vectors that are along the plane? And you can do that, but you would need 2 vectors, okay? You can't just do with 1 vector. You would need 2. And again, this is all extra. So you could ignore it. If you get confused easily, just go ahead and ignore it. But we can actually describe points on a plane using the prescription of vectors along the plane. If we have R naught here, which points to a point along the plane, well, we could add any combination of U and V to get points. For example, if I wanted the point that points to this point on the plane, then that one is going to be R is equal to R naught, the purple, plus U plus V. Okay? R naught gets me to gets me up to the plane. And then I move to U, but I'm not done. I want to move down to this point here. So I'll also then add V. Okay. And in fact, any point that you choose, any point whatsoever along that plane, you could describe as some sort of multiple of V and U. Okay. So you would have this type of relation. Again, this is not to be really used, not used in class. In our class, but I like to show you all of the different perspectives that you could get, and I think that's useful for just a deeper understanding of the topic. But if you just want to learn how to compute, well, I'm also very happy to work with you in that regard. So that's just an alternative description.